Alright everybody, this is our second video about gas laws, and this video actually is going to talk about something called the ideal gas law. It's somewhat more involved than the simple gas laws we saw before, because for each of those three, if you remember, they only compared two variables each. The ideal gas law is more involved because it actually compares all four: pressure, volume, number of moles, and temperature. Alright. So the three simple gas laws that you hopefully just watched about were used when you had a set of initial and final values, and you had to figure out one given the other three. The ideal gas law is for something different. It allows you to calculate one of the four variables between pressure, volume, number of moles, and temperature given the other three. Alright, so the ideal gas law and the simple gas laws do two different things. Now, you might think that means, well, I've got to memorize a whole bunch of different formulas, and well, that sucks. Well, okay, yes, it might suck if you did it that way. There is, however, an easier way to do it. You can get the three simple gas law formulas from the one single ideal gas law formula. That's one cool thing about it. So there's only really one formula to learn. So let's just talk a little bit about what that ideal gas law is. Alright. Pressure is, of course, just pressure. These units we always want to show when we're using the ideal gas law in atmospheres. Volume we always want to show in liters. Number of moles is, of course, moles. Temperature, as we said before, was Kelvin. Now, if you remember previously, I told you that for the volume and the pressure, it wasn't all that important to convert the units into atmospheres or liters, but it was a good idea to practice that. Well, the reason why is coming up right now. It's this guy right here. This is something called the universal gas constant, and that allows for the correlation of pressure, volume, number of moles, and temperature with each other. Simply because temperature has units of Kelvin, N has units of moles, V has units of liters, and P has units of atmospheres. So there has to be a way to get all those units to cancel each other out. And there is. If you were to solve for R, so take N and T and divide them underneath here, and you're under standard temperature and pressure conditions, where you had a pressure of 1 atmosphere, a volume of 1 liter, 1 mole, N equals 1 mole, and a temperature of 273 Kelvin, which is standard temperature. Plug all those into your formula, get out a value of R, and what you would get out would be R is 0.082. And then the units, if you took N and T over here, you'd have pressure and volume on the top, which would be atmosphere liters. And then on the bottom would be moles and temperature. So atmosphere liter, or liter atmosphere per mole per Kelvin. This is the universal gas constant, and it's an important thing for you guys to know. Alright, you'll be given this on a quiz, but it's important for you to know what it's for. Alright. Anyway, so the ideal gas law relates pressure, volume, number of moles, and temperature to each other. Now, before we get into actually doing an example of a problem using the ideal gas law, because it's not all that complicated to use, I do want to just show you what I said before, that you can get the three simple gas laws from the ideal gas law. In order for us to do that, we have to write out the ideal gas law as such. You remember the simple gas laws related a set of initial and final variables together. So I've written the ideal gas law out in initial and final variable form. So if we look at Boyle's law first. Boyle's law. Alright, now from the previous video, one thing you'll have seen about Boyle's law is that The equation for Boyle's law is P1 V1 equals P2 V2. But that assumed conditions of constant temperature and number of moles. All right. R is a constant. So what we're going to do here is we're going to take out the variables that are we're going to take out the variables that are constant. R is constant, so we're going to take that out. Temperature is constant, so T1 equals T2. Number of moles is constant. All right. So that means N1 R times T1 is the same as N2 times R times T2, which then allows us to say if those are equal, then P1 V1 equals P2 V2. So what we've just done is go from the ideal gas law to the equation for Boyle's law. Now when we go down here to Charles's law, all right, Charles's law compared volume and temperature. V1 over T1 is V2 over T2. But that assumed constant pressure, number of moles, and of course R as before. So if we cut out the things that are constant again, cut out number of moles as well, and then cut out the pressure, what we're left with is V1, T1, V2, and T2. All right, and we can rewrite that by saying V1 over T1 is the same as V2 over T2. So again, what we've done is we've come up with the relationship between pressure, between volume and temperature. All right. And then when we went down to Avogadro's law, which said that the volume and number of moles were related to each other directly, all right, and that assumed constant pressure and temperature, and of course the constant R. So when we cross out the constants here, we have a situation that's similar to what we had up here, and we can rearrange that to say V1 over M1 equals V2 over N2. So the point here is we've shown that we can get information for each simple gas law from the ideal gas law. The other way to look at it is if we cancel out up here the N, the R, and the T, we're left with pressure and volume equaling pressure times volume, which means they must be inversely proportional, which is exactly what we said before. Pressure inversely proportional to volume. And when we go over here, we're saying that volume and temperature are actually directly proportional as they are over here, which again is exactly what we saw in the previous video. And again, for Avogadro's law here, when we cancel out all the things that are constant, volume is directly proportional to number of moles, which is again what we saw previously. Anyway, let's actually get to working a problem using the ideal gas law. So notice this does not say anything about initial and final variables. It tells us to find the pressure. So we've got to find the P. We're given the amount of gas, which we're going to convert into moles. We are given the volume that we've got to convert into liters. We're given a temperature that we've got to convert into Kelvin. All right. Notice we're not given the gas constant. That is right here, 0.082 liter atmospheres per mole per Kelvin. So we know the ideal gas law looks like this: PV equals nRT. And we are solving for P. So we know therefore the formula that we're actually looking for to use is this one. But I also said we have to make sure our units are all converted into the correct ones. So pressure is what we're looking for. All right. And let's make this a little bit more interesting. Let's find this pressure in millimeters of mercury. Alright. Anyway, so our N. Is our N in moles? Well, no, it's not. Our temperature, is our temperature in Kelvin? No. Is our volume in liters? No. So actually we have to convert every variable. Let's do the simple one first. 648 mils is of course 0.648 liters, knowing that there's 1,000 mils in a liter. Temperature is 32 plus 273, should be 305 Kelvin. The number of moles is a little bit more involved, but it's not that much more. We have 0.133 grams of helium. And all we've got to do is convert it into moles. And we can use the periodic table to tell us that 1 mole of helium weighs 4 grams. So therefore the number of moles here of our helium is actually 0.03325 moles of helium. Then all we have to do is to say plug everything in. Our N is 0.03325 moles. Alright, our R is 0.082 liter atmospheres per mole per Kelvin. Notice I'm putting the mole per Kelvin on the bottom. I'm doing that just so we can make sure we can cancel out all our units. Our temperature is 305 Kelvin. And our volume is 0.648 liters. Alright? So let's see what we can do with those units. We're looking for atmospheres, so everything else should cancel. Liters cancels, moles cancels, Kelvin cancels. Alright? So what we end up with is an answer in atmospheres of 1.28 atmospheres. But what if we're asked to find that pressure in millimeters of mercury? Well, you need a conversion factor for that. And the conversion factor is this. 1 atmosphere is equal to 760 millimeters of mercury. So when we plug that conversion factor in, 760 millimeters of mercury over 1 atmosphere, and then calculate that out, what we get is 975 millimeters of mercury. That is the answer. That's how we use the ideal gas equation, the ideal gas law. We solve for what we want, we convert whatever units to the standard units we need, and then we find what we need. Alright, thank you.